Welcome back. In this video, we will explore the Cuk Converter. So design the simulation of Cuk Converter in MATLAB Simulink. First, we will explore the Cuk Converter. It is a unique DC-DC converter that can both step up and step down voltage efficiently. It is also called as modified buck boost converter. So here, the output polarity is reversed with respect to the input. So that is meant by we will give the positive voltage, we will get the negative voltage. So it is mainly used applications in the field of renewable energy applications. So to design the Cuk converter, so mainly we will need L1, L2, C1 and C2, 4 commons. So these are the 4 commons are very important for the designing of a Cuk converter. Here C2 will act as a voltage regulator, does not affect the design of this Cuk converter. So the Cuk converter operation is mainly depends on the how the capacitor C1 is charged. So based on this operation, it can be act as a Cuk converter. That is mean the polarity reversal happen based on this capacitance charge. Okay. So this Cuk converter combines both the feature of buck and also boost. That is mean by if the input voltage is low, the output voltage is higher, it will act as a boost converter. If the input voltage is high, the output voltage is low, it will act as a buck converter. Working principle of Cuk converter. It operated in 2 modes. One is switch on mode, another one is switch off mode. First we will discuss about a switch off state. During the switch off state, this switch will be open circuit. So therefore, energy stored in capacitance will discharge through this diode. This diode becomes forward bias due to the reason of this maximum stored energy in capacitance. So therefore, the inductance current will discharge through the L1, C1 through D1. So we will get current direction like this way. So therefore, voltage Vs is equal to across the voltage across the inductance VL1 plus VC1. So therefore we can get the capacitance voltage VC1 is equal to Vs minus VL1. So now during this time, the inductance stored energy will discharge through this way. So similarly, stored energy in inductor 2 will discharge through L2, then D1 and also load resistance R. Now the polarities becomes a positive and here we will get negative. So look at the input side, we get the input polarity is what? Positive and also negative. The output polarity is in denominator side, lower end side we will get positive, in numerator we will get what? Negative. So therefore the output polarity is reverse. So that's what we will give the positive supply to the input side, we will get what? Opposite polarities of the output side. So during the on state, when switch S1 is turned on, so this diode becomes what? A reverse bias. So therefore, this diode will be open circuited. Now the input supply flow through the L1 and also switch. So during this time period, L1 stores the energy, and also here the secondary side. Now the capacitance C1 will discharge the current through the switch and also load resistance or through the L2. So it is also a reverse side. That is going to be polarity is positive. Here also what? Negative. Here the C2 will act as a voltage regulator. We will move to design of Cuk converter in simulation. Today we are going to design a boost type of Cuk converter. So I have referred formula from the journal to design a Cuk converter. So these are the formula of Cuk converter for. So first one is duty cycle. To calculate the duty cycle D, I refer D divided by 1 minus T. So the D value is calculated with respect to V0 and also depends on Vs, that is going to be output voltage and also input voltage. Similarly, inductance L1 is calculated as with respect to supply voltage and a duty cycle divided by switching frequency and also current. Then similarly, L2 will be calculated as similar input supply voltage, duty cycle D divided by switching frequency and also inductor current L2. Then similarly capacitance value with respect to output and also duty cycle. Similarly capacitance C2 value will be calculated like this. So to understand this one, first we need to choose the input voltage. So in my simulation I chose the input voltage is, look at here, 12 voltage. So the design of boost mode in Cuk converter, I choose the output voltage is 24 volt. So therefore the output voltage is higher than the input voltage, and also I take as the power is equal to 200 watts. So I choose the switching frequency is equal to 10 kilohertz, and also to calculate the duty cycle of D, I referred V out divided by V in plus V out. So refer from this formula converter, I choose D is equal to V naught divided by V naught plus V in. So that's what I have mentioned here. Similarly, I in max to calculate the IL1 to calculate the IL1, I choose that first I in max current. So therefore power divided by V input, I calculate the I in max. Similarly I calculate the I out max is equal to P divided by V out. Similarly the load resistance value is calculated based on the V output voltage divided by I out maximum current. So therefore I choose the del IL1, del IL2, del VC1 and also del V0. These values are I choose with respect to of ripple current. So I referred here 0.1 with respect to I in max. Similarly del IL2 chose 0.1 into I naught max. Similarly del VC1 and also del VC2 similarly choose like that. It is represented as 10% of ripple current, that is meant by 10 divided by 100. Then L1 value will be calculated V in into D divided by del IL1 into switching frequency. So referred in this formula V in, that is meant by supply voltage, and also switching duty cycle divided by switching frequency and also del IL1. Similarly L2 will be calculated. So that's what we referred here. L1 is equal to V in into D del IL1 into switching frequency. Similarly L2 then capacitance C1 and also C2. So to run the simulations, we will get the values of capacitance. So look at here, the capacitance value in workspace. So C1 is equal to 4.629 e power minus 0.4 farad, and also C2 is equal to 4.34 microfarad, and the duty cycle ratio D is equal to 0.6667. Similarly del IL1, del IL2, del VC1, del VC2. So this is the watt switching frequency we have chosen in our simulation, that is nearly equal to 10 kilohertz, and L1 value we calculated 4.8 and e power minus 4 Henry. Then also L2 is equal to 9.6 e power minus 4 Henry. We choose the power is equal to 200. So this simulation is based on the how much power we choose with respect to input and also output. We get the different types of value of capacitance C1, C2 and also L1, L2. The load resistance is depends on how much we choose the output power P. So okay, now we design the values of C1, C2, L1, L2 and also load resistance. In this case, now we are going to simulate the Simulink. So first we record the input supply. So for the input supply, I choose voltage source, and also the input voltage I mentioned in my simulation, it is a 12 volt. So here is 12, and also the final value is also 12. So step time I taken as a 0, then apply. Then so look at the Cuk converter circuit model. It is a 2 inductance and also 2 capacitance and also 1 MOSFET or IGBT, that is in base switch, and another one is a diode. So let us choose a inductance RLC branch. So we will take series RLC branch from the MATLAB history. Then after that set the values of I mentioned as L1. So choose the common as a inductance L, just you mention here L1. It refer the value directly from our base workspace. Then apply. Then similarly choose the another components. Next one is capacitance. So change this one is to capacitance. So here choose the value of C1, apply. Similarly, all the 4 components has been selected. So choose the components of L2, component of L, and apply L2. Then apply OK. Then next component, it is a capacitance. Choose C and also C2. Apply OK. So rotate the components. Then connect all the components one by one. Then next, choose the load resistance as a resistive load. Choose resistance component R. Apply R and also set apply OK. Then connect all the components with respect to our circuit diagram what we chose in Cuk converter model. So now we connected only switch and also diode only remaining thing. So I connected diode, so connects the diodes between the C1 and also L2. Then connect the switch in between L1 and also C1. So I choose IGBT. So rotate the components. So connect between this one. Then after that, choose the switching frequency for gate. So with respect to PWM generation, so I choose a PWM generator. Connect the components to the PWM generator, and also the duty cycle. We have designed the duty cycle. So take a constant black. We already calculated the value of D. So just mention here D. It will take a value from workspace. Then apply OK. Now we need to connect the scope across the resistance. So I choose the voltage measurement and also current measurement. So to calculate the current through this resistance, the ammeter is connected in series with the load, and similarly the voltmeter is connected parallel with the load resistance. Then I choose the scope. So first one, load voltage. Second one, we connect into load current. Now we set the input voltage is equal to 12 volt, and also the switching frequency we have applied here. It is a Fs. It taken from 10 kilohertz, and also we designed the duty cycle D. We gather from the workspace, and also L1, L2, C1, and also C2. This is the load resistance RL. So I will choose a display. So to the how much current and also how much voltage I am getting from this work. So now run the simulation. So I choose the time period is of 5. Now run the simulation. The input voltage is equal to 12 volt. So look at the output voltage is nearly equal to minus 23 voltage. So it is a open loop connections. So still we are not getting the current value is nearly equal to 8.2. So if we multiple voltage and current, we will get nearly approximately equal to 196 watts similar. So this simulation is designed for 200 watts. So look at the waveforms of Cuk converter. You can see here it is nearly equal to minus 8 and also minus 23 to minus 24. This yellow color is indicates a load voltage, and this blue color is indicates what? Load current. Suppose if any changes in the input voltage, so suppose I introduce here some changes in step time 1, I will introduce here more to voltage 14 voltage. So automatically our design will be affected because we choose the input voltage is 12 volt and the output it is nearly equal to what, 24 volt. If I change the if the input voltage is increased to voltage, automatically the inductance value capacitance will be varied. So look at our simulations. So in order to maintain a constant voltage in output side, we need to introduce a what? PAD controller. So therefore, in order to introduce a PAD controller, this constant duty cycle will be removed. So look at the exact one time period. So now the time duty cycle is near time cycle 1. Then after that, look at here, the input output voltage is slightly increased to minus 28, and also look at the current. So this will happen due to the slightly changes in the input side. So this will affect the output constant voltage. So in order to avoid that, we are moving to PAD based PWM generator renewable energy applications, because solar panel will vary the output voltage with respect to irradiance level. So in order to that conditions, we need to give a constant duty cycle to the variable duty cycle to the IGBT. Okay, so I am introducing a PAD controller for this case. So we will take as a constant voltage is equal to 24 voltage. So I am going to just reverse the polarity because I am getting the negative value. So I am going to change this slightly change the connections. So I connect the ammeters as a -1 to capacitance C2 side, and positive terminal to the voltage side, and positive end to the this one, negative end to this one. So now I will get the reverse polarity, that is maybe a positive value. So this output voltage is a reference, this output voltage is a actual voltage. I connected with this output voltage, and also my reference is voltage is what, 24 voltage. I connected this error detector with the PAD controller. Then after that I remove the fixed duty cycle to the variable duty cycle D. So now we run the simulation. You can see the output. So I already designed the value of PAD. That's what I'm not shown here. So I didn't tune properly, so therefore I will get a slightly error in my output. So it is nearly equal to 23 to 24, approximately is equal to 24. But we know, so look at the one period, our output will be nearly maintained what, 24. Slightly the current is it's also nearly equal to 8. So look at the waveforms. So we introduced a error at the input side. We introduced a error at the input side. I stop the simulation. So look at here, just we introduce a error in the input side, so slightly it will increase to that input voltage, and then after that it will be rectify the errors and maintain the same output voltage. So this is the input side condition. Suppose if load increases in the output side, it need to be maintained the same 24 voltage in the output side. So therefore, in order to understand that, I am going to introduce another one error in the output side. So therefore, I remove this one, and also I add another one switch, ideal switch with respect to this resistance, and also I give the time period to this switch, and this negative end will send to the this one, and similarly another one load, additional load will be added here. So this one is connected to the this resistance, and also this resistance will be connected to here. So I set the load exactly 0 to 3, one amplitude will be increases, and here the same will be maintained here. So look at the changes in our simulation. So we introduce a two error at a time period of 1 second. We introduce a two more additional voltage in input side, and also I added another resistance here at a time period of 3 seconds. So we introduce a 2 error, and also we want to check the output voltage to be maintained as a constant. So at period of 1 second we maintain the same thing. The simulation is nearly equal to 3 seconds. Look at, we introduce another one load in additionally. So now look at here. So it is nearly maintained the same voltages. Okay. So look at here. It is nearly maintained the same voltage at the output end. But I didn't tune the current controller, but I chose the error as a voltage 1. Okay. So it is nearly equal to 24 voltage. So this is the operation of closed loop controller of Cuk converter. I hope you understand how to design of Cuk converter in simulations, and also how to simulate the Cuk converter in Simulink. Thank you.